we all have a notion, some notion at least, as to what relative motion is. If I'm on a train and the train is moving at 30 kilometers per hour and I'm walking at 5 kilometers per hour in the direction of the train, then my velocity relative to the train is 5 kilometers per hour. My velocity relative to the Earth would be 35 kilometers per hour if I'm walking in the same direction as the train, right? We all have this notion of what that means, relative motion. Relative to what? Relative to the train, relative to the Earth. What if you're walking in the train at 5 kilometers per hour, though, perpendicular to the way the train is going? We're still going to add together the two velocities to get the velocity relative to the ground, but we have to add them together differently. We have to add them together vectorially. When we add two numbers vectorially, then we have to get a vector diagram, right? It's the idea of getting that right-angled triangle and then solving that right-angled triangle using the Pythagorean theorem in the inverse tan function. So, when we're solving a two-dimensional relative motion problem, it boils down to getting a right-angled triangle. The trick now is remembering which vector is which. Which vector is what we call a solid line vector, and which vector is what we call a dotted line vector. If you remember, the solid line vectors are those vectors that contribute to where we go. For instance, when we aim in a particular direction or head in a particular direction, that's not where we're going. I mean, it could end up being where we're going if there's no wind or anything. But if there's any other factors involved, we don't go where we aim. We don't go where we head. That's a solid line vector because that contributes to where we go. Similarly, wind speed or a river current, if we're going across, swimming across a river, swimming across somewhere where there's a current. In the end, that wind speed or that river current isn't where I end up going. If the river current is directly south, well, then I end up being carried by that river current. But if I'm aiming in another direction, I go somewhere in between. So it contributes to where I go. The airspeed, how fast an airplane could travel without wind, contributes to where I actually go. The dotted line vectors are where I do actually go, or at least where I want to go. The pilot of a plane wants to head directly north to Edmonton. Okay, the captain of a ship wants to head directly east across the lake. Where we want to go, or where I actually end up going, or sometimes we say the ground velocity. The velocity of the guy in the train relative to the ground. Those are all dotted line vectors. They're all resultant vectors. All right, you last week had 3 questions on a worksheet that you were working on. And we checked over that worksheet. Was there any issues that we haven't addressed with those 3 questions? You guys feel comfortable with that? Yes? You guys are comfortable with those 3 questions, and I want to take a look at another example here. This says the pilot of an airplane wants to go directly north at a velocity of 500 kilometers per hour, but there's a wind blowing to the east at 85 kilometers per hour. What's the velocity, including the direction that the pilot must aim the plane in order to accomplish this? We said last week, hey, wouldn't it be useful if you were a pilot to know some vector analysis, or the captain of a ship to know some vector analysis? Yeah, it would, for sure. If you aim to the north and there's a wind to the east, it would be useful to know where you're going to end up going. What would be more useful to know is how to avoid going off course. If you want to head north, how do I end up going north? Right? What do I get to do to end up going north? That's what we're doing in this question, right? Where do I have to aim in order to go directly north? So let's look at our vectors here. We've got wants to go directly north at 500 kilometers per hour. Is that a solid or dotted line vector? Does that contribute to where I go, or is that where I go? Solid line vector. So where I want to go contributes to where I go. Where I want to go is hopefully going to be where I go. Right? That's a dotted line vector. So we're going to draw that 500 kilometers per hour north as a dotted line. There's a wind blowing to the east at 85 kilometers per hour. That definitely contributes to where I go, the wind, right? So we're going to draw that 85 kilometers per hour like this to the east. Now the only question now is where do I draw that relative to my dotted line? I'm going to give you 4 options here. Option 1, option 2, option 3, or option 4. 2 of them actually work, 2 of them don't. 1 of them is best though. Where do you want to draw that position? 1, 2, 3, or 4? Cody? Position 2? Let's get rid of all these. Does that work, guys? That work? Hey, he's got this drawn front to back, right? There's a problem with that though. What's the problem with drawing it front to back here? My dotted line vector isn't supposed to be drawn front to back, is it? It's the resultant vector, so it's supposed to be drawn start to finish. It's drawn toward the start here, Cody, right? Not towards the finish, right? Does that make sense, guys? So that's not going to work. Okay, so let's redraw 1, 3, and 4. Got to be one of those 3 positions now. Which one do you want to pick? Caitlin, it looked like you were ready to raise your hand, but maybe it was just to scratch your cheek there. Kenzie? Option 1. Does that work, guys? Look, that's drawn front to front. Mackenzie, is that okay? Good. Yeah, because it's the dotted line vector, it is okay. The other option, by the way, would have been 4, 1, or 4. Because remember, the dotted line has to be drawn start to finish. That's drawn to the finish. Okay, at vector 4, it's drawn from the start. I'm suggesting that you always draw it to the finish. That means that the other vector, by the way, the value of that was, what is it, 85? The other vector that we have to draw is this way. Is that dotted line drawn start to finish? Yes. Are the solid line vectors drawn from front to back? Yes. Does it make sense? If we take a step back from it, forget about the physics behind it, let's look at the intuition behind it. Does it make sense? If there's a wind to the east, and I want to go directly north, where do I have to aim? Well, if there's a wind this way, and I want to go this way, then I'm going to aim up here somewhere, right? That makes sense? When you're driving down the highway, driving into Calgary, and there's a wind blowing from the mountains, blowing to the east, your steering wheel ends up, if you look at your steering wheel, it always ends up like it's going partway to the west. You have to go against the wind to counter that, right? That's what we're doing right there. So there's a way to look at this, like Mackenzie did and said, oh, look, it's got to be drawn front to front because one of them is a resultant vector. But you can also kind of look at it and say, intuitively, I know that the vector that I want to solve for, where I aim, has got to be this way. That make sense? All right. I'm just going to replace this over here because I don't want you to get mixed up with which one that means. That's 500. This is the hypotenuse again, right? This is the angle. Mathematically, this isn't any harder than anything else we've done. Just drawing the diagram was a little bit harder. So let's find the value of C. It's the square root of 85 squared plus 500 squared. Theta is the inverse tan function of opposite over adjacent, which is 85 over 500. Anthony gets 9.6 degrees. We're going to say that's what of what? North of south, west of southwest. What is it? We got a north. Yeah. We're going to say it's west of north. Good. Now, this gets a little bit confusing, right? Because our vectors are north and east, right? But we didn't go north and east. We went north and west. And we're measuring it west from the north here. So you're right. It would be west of north. Good, Cody. What's the value of C there, this side of the room? Brianna, do you have that? 98? I think you might have made that 85 and 50 maybe, instead of 500. Okay, that's okay. Yeah, Zach? 507.2, or I'm going to round that to 2 digits because of this. 5.1 times 10 to the 2. So this pilot has to aim at 5.1 times 10 to the 2 meters per second at 9.6 degrees west of north. Good. For the next little while, you're going to take a look at pages 2 and 3 of your worksheet booklets. Pages 2 and 3 of your worksheet booklet is questions 4 all the way up through question 7, please. Let's take a look at question number 5 from your worksheet now. It says the captain of a ship aims his ship with a velocity of 25 meters per second directly north across the river. He aims the ship at 25 meters per second across the river. That's a solid line vector. He aims 25 meters per second. Now, there's a river current that flows at 8 meters per second to the east. That's a solid line vector as well. Solid line vectors go front to back. So I'm going to draw it exactly like this. Now my resultant vector, which is where I actually go relative to the shore, that's going to be my dotted line. That's where I go. Now I'm going to draw in a little bit more here. This is the river, right? I'm aiming directly north across the river at 25. There's a river current to the east at 8 meters per second. There's something else that I have here, and that's the width of the river. That's not going to help me in question A, because it doesn't form part of the vector diagram. Don't ever mix velocity and displacement in the same vector diagram. Okay, if you're drawing a vector diagram for velocity, great. If you're drawing it for displacement, great. But don't put 850 and 8, for instance, in the same diagram, because they don't go together. Okay, this is my vector diagram that I'm going to use for question A, and then this is just something I know, so I'm writing it down just in case it helps me later on. For question A, we want to find the velocity of the ship relative to the shore. So we're going to find C, the hypotenuse, along with the angle at the very beginning here. Call it theta. We're going to say to find C, it's the square root of 25 squared plus 8 squared. And we're going to say for theta, it's equal to the inverse tan of opposite over adjacent. That's 8 over 25. Okay, what do we get for C there? Just because your hand up there, do you have the value of C? 26 meters per second. What's the unrounded number in case we need that later on? Yep. 26.2 meters per second, which, Jessica, you're right. We're going to round that to 2 digits for a final answer. I just wanted in a couple decimal places just in case we need to use the number later on. So let's round it there as a final answer now in A, 26 meters per second. The angle works out to be what? Yep. 17.7 degrees. No, that's right. That's right. But we're going to round it to 2 digits for a final answer. You're absolutely right about that, Mackenzie. But the more decimal places we have written down, the better, in case we need to use the number for B or C. Then we want to use the unrounded number, right? So that's going to be 18 degrees. That's going to be west of north. Now, it's conceivable that somebody could have drawn it like this, right? In that case, you would have gotten 26 at 72 degrees north of west. Anybody get that? 72 north of west? Okay, that would have been correct as well. Yep. Yes, it should be. Thank you. Yeah. East of north is right. Because, of course, you're going to the north, but it's measured east from north, not west from north, right? All right, question B. This is where the challenge is. Mathematically, it's easy. It's just a matter of figuring out what to do, right? B says, how long does it take to get across the river? Now, a number of people come up with the equation V is equal to delta D over delta T. They assumed it went at a constant velocity, which is a pretty good assumption. Okay, good. V equals D over T. And then they said, well, let's rearrange that to solve for T. T goes up by multiplying, the V goes down by dividing. This is what we have for an equation. And then people said, almost everybody said, D is 850, right? It's the only displacement I have. Good, that's what I would have done too. Here's where people made a mistake. Almost everybody at this point said the velocity is 26.2. What's wrong with that? What's wrong with using 26.2 now, can we? Right. That velocity is a diagonal, and we don't have a displacement at the diagonal. We have a displacement straight up, right? Guys, remember from the very second day of Physics 20, whenever we were using this equation, this value and this value had to be the same direction, right? Displacement and velocity were always in the same direction. They have to be. So if I'm using a displacement directly north across the river of 850, then I have to use a velocity directly north across the river of 25 meters per second. Now Ethan did it a little bit differently, which was okay. A tiny bit more work, not a lot. Okay? Just as good of a method as mine, just was slightly different. Ethan's used the same equation, delta D over delta D over V, but he used the value for the velocity diagonal, 26.2 meters per second. How did he use that and still get the right answer? Well, because he used the displacement at the angle as well. Ethan, what did you have for that displacement? 892? So Ethan said, look, I know the angle, okay? I know the adjacent side. I can find the hypotenuse in terms of displacement, and then I can say angle displacement over angle velocity. Okay, that's fine. I said north displacement over north velocity. Both of them give us the exact same answer. It worked out to be, I think, 34 meters per second. Yes, it is seconds, yeah. I was looking at this over here, right? But it's, we rearranged that. Thank you. 34 seconds. Once you have this, C's not so bad. C said, how far downstream do you end up going? Downstream is this way. In other words, I want to find a displacement in the x direction. This displacement right here. If I want to find that displacement, what velocity do I have to use? The x velocity, right? Which was 8 meters per second. Okay, whatever direction my velocity is in will be the direction of my displacement. If I want to find x displacement, I got to use x velocity. If I want to find y velocity, I got to use y displacement, and so on. The time here, by the way, would be what? Wait a second. You're right, by the way. Answer this one for me, please. Please help me out with this one. Why is it okay to use 34 seconds for the y direction and the x direction, but it's not okay to use the same velocity or the same displacement for x and for y? Good. Time's a scalar. Okay, so you can make that transition from x to y easily with time because it's a scalar, the directions are relevant. Okay, when we're talking about displacement or velocity, it has to be x or y. Does that make sense? I don't know what that works out to be, guys. 8 times 34. 272 meters, thank you, which technically we should round at 2 digits. 2.7 times 10 to the 2 meters to the east, right? Homework for tonight, guys. Finish your worksheet.